Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 6, 2026, just about a week ago. It introduces a generative meta model trained on 1 billion neural activations that significantly improves our ability to steer large language models without degrading their output quality. The paper is titled Learning a Generative Meta Model of LLM Activations, and as we'll see later, the results on scaling and interpretability are really impressive. Figure 1 illustrates the complete pipeline for the generative latent prior. Panel A shows the training phase, where activations from a language model are corrupted with noise and then reconstructed by a diffusion-based activation model. Then, Panel B visualizes the inference process. Typically, steering interventions perturb the model state off the natural manifold, shown here as the pink region, but this method projects it back to valid territory. Finally, Panel C proves the benefit, comparing a standard sparse autoencoder that produces repetitive loops against this method, which successfully generates fluent, on-topic responses. Alright, moving on to the results. Figure 2 demonstrates that this meta-model scales predictably with compute. Panel A plots the diffusion training loss against floating-point operations, revealing a smooth power law curve where the loss drops steadily as resources increase. Crucially, this translates directly to utility. Panel B shows that steering performance, which balances concept accuracy and fluency, improves in lockstep with that additional compute. Similarly, Panel C indicates that the model's ability to probe for internal concepts also rises consistently, suggesting that bigger models will yield even better interpretability tools. So, while Figure 2 showed the scaling trends, Table 1 now quantifies the generation quality using Frische distance. This metric tracks how closely generated activations match real ones, with lower scores indicating better quality. Looking at the Llama 1B section, the standard sparse autoencoder reconstruction scores nearly 2.0. In contrast, the generative latent prior beats this easily, starting at 0.68 with 3 layers and dropping to 0.53 with 24 layers. This is remarkable because the generative model works from pure noise, while the autoencoder has the easier task of reconstruction, yet the generative approach still captures the distribution more accurately. Well, Figure 3 visualizes this generation quality directly. Here, the yellow dots represent real activations from the dataset, while the pink dots are samples generated by the model. In panels A and B, where the system uses only 1 or 4 sampling steps, the generated points fail to cover the real distribution. However, looking at panel C with 20 steps, the pink cloud expands to overlap the yellow one almost perfectly. Panel E confirms this quantitatively, plotting the Frechet distance which drops sharply and flattens out at 20 steps, proving the model quickly learns the true shape of the activation manifold. While the previous figure focused on visual distribution, Table 2 measures the actual impact on the model's performance using delta LM loss. This metric tracks how much the language model's perplexity increases when we replace its original internal states with reconstructed ones. For the Llama 8B base model, the standard sparse autoencoder causes a loss increase of roughly 0.20. In contrast, the generative latent prior keeps this disruption 4 times lower at just 0.05. We see a similar advantage on the instruct version, proving that the generative approach stays on the valid manifold much better than sparse methods. Alright, moving on from the reconstruction metrics, Figure 5 demonstrates how this translates to actual model control. This chart maps the trade-off between output fluency on the bottom axis and concept strength on the vertical axis. The yellow line represents standard sparse autoencoder steering, which hits a ceiling where pushing for a stronger concept quickly destroys the text quality. By contrast, the pink line shows the performance when using the generative latent prior. Because it projects activations back onto the valid manifold, it extends the trade-off curve significantly higher, allowing for much stronger steering without devolving into gibberish. So, having seen the steering benefits, Table 4 now evaluates how well these models isolate specific concepts using one-dimensional probing. This test measures if a single internal feature can predict concepts, like whether a text is about biology. For Llama 1B, standard sparse autoencoders score 0.70, while raw neurons reach 0.79. However, the generative latent prior tops them at 0.84. This trend holds for Llama 8B, where the generative model hits 0.87. Remarkably, the small model's generative features actually outperform the raw neurons of the much larger model, proving they capture cleaner semantic concepts. Wrapping up, 2 main takeaways stand out. Generative metamodels provide a much richer map of an AI's internal state than traditional linear tools, and they scale predictably with compute. This implies a reliable path forward, where larger diffusion models unlock deeper transparency and precise control over large language models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.